Sound waves, which are longitudinal waves, propagate with the vibrations of the particles of a medium in the direction of propagation of the waves. Sound waves in air consist of propagating compressions and rarefactions of small volume elements of air. In the region of compressions, there is an increase of pressure delta P, due to which the volume V of the elemental volume decreases by delta V. The volumetric strain of the elemental volume is denoted by the ratio between delta V and V. Bulk modulus B is expressed as the change in pressure by volumetric strain, which is equal to minus delta P by delta V by V. Let this be equation 1. The SI unit of pressure is Newton per meter square or Pascal. The dimensional units of pressure P are kilogram meter per second square into meter raised to the power minus 2. That is, the product of M, L, T raised to the power minus 2 and L raised to the power minus 2. Dimensional units of change in the pressure delta P is equal to the product of M, L raised to the power minus 1 and T raised to the power minus 2. Let this be equation 2. In the region of compressions, there is an increase of pressure delta P. There is a decrease in volume delta V and an increase in density. The dimensional units of density are kilogram per meter cube. That is, the product of M and L raised to the power of minus 3. Let this be equation 3. Let us now find the dimensions of bulk modulus B by density ρ to arrive at the dimensions of velocity V. From equations 2 and 3, we get B by ρ is equal to M, L raised to the power minus 1 and T raised to the power minus 2 by ML raised to the power minus 3. B by ρ is equal to the product of L square and T raised to the power minus 2. This can be written as L into T raised to the power minus 1 whole square, which are the dimensional units of V. Therefore, V can be written as the product of C and root B by ρ, where C is a dimensionless constant, which is equal to 1. This can be written as V is equal to the root of B by ρ. Let this be equation 4. Equation 4 implies that the speed of a longitudinal wave in a fluid depends only on the bulk modulus and the density of the fluid. Instead of a fluid, if you consider a solid bar as the medium, Young's modulus Y is used in place of bulk modulus B, as sideways compression or expansion of the bar is negligible. Only longitudinal strain is considered and the equation is modified to V is equal to root Y by ρ. Let this be equation 5. The table shows the speed of sound in various media. From this table, we find that the speed of sound in liquids and solids is higher than in air. The reason is that the densities of liquids and solids are higher than the density of air. Liquids and solids are less compressible than air, and therefore have a greater bulk. Liquids and solids are less compressible than air, and therefore have a greater bulk modulus, resulting in a higher value of B by rho. Newton tried to find the speed of sound in an ideal gas. Assuming that the gas undergoes isothermal changes while a sound wave propagates through it. Isothermal refers to equal thermal conditions, meaning a constant temperature that is maintained while energy propagates through the gaseous medium. For an ideal gas, under isothermal conditions, the relationship between pressure P and volume V is expressed as PV is equal to the product of NKBT, where N is the number of gas molecules in volume V, Kb is the Boltzmann constant, and T is the absolute temperature of the gas. The quantities on the right-hand side of the equation are constant. Hence, PV is equal to constant. The above expression leads to delta PV is equal to 0. This implies that V delta P plus P delta V is equal to 0. This can be written as V delta P is equal to minus P delta V. V delta P by delta V is equal to minus P. Once again, this equation can be written as delta P by delta V by V is equal to minus P. Therefore, minus delta P by delta V by V is equal to P. The left-hand side of the above expression is nothing but the bulk modulus B of the gas. Substituting this in the equation for the velocity of sound in air, V is equal to root P by rho. Let this be equation 6. Thus, the speed of a sound wave in an ideal gas is denoted by equation 6. As this equation was given by Newton, it is called Newton's formula. Let us now calculate the velocity of sound in air using Newton's formula. The density of air is the product of the mass of 1 mole of air and its volume. Let this be equation 1. Mass of 1 mole is 29 into 10 raised to the power minus 3 kilograms. And its volume is 22.4 into 10 raised to the power minus 3 meter cube at standard temperature and pressure. By substituting the values in equation 1, we get rho is equal to 1.29 kilograms per meter cube. We know that atmospheric pressure P is equal to 1.01 into 10 raised to the power 5 Newton per meter square. Substituting the values of 2 and 3 in Newton's formula, we get the velocity of sound in air at standard conditions of temperature and pressure, according to Newton's formula, is V is approximately equal to 280 meters per second. But the experimental value of the velocity of sound in air at standard temperature and pressure conditions is nearly 331 meters per second. This means the value derived from Newton's formula is about 15.4% less than the experimental value. This variation in magnitude in the experimental value and the calculated value cannot be attributed to experimental errors. Hence, there arose a need to revisit Newton's assumptions on deriving the expression for velocity of sound in gases. It was Pierre-Simon Marquis de Laplace, a French mathematician and astronomer, who pointed out that the speed of sound in air depends on the heat capacity ratio. This is because the changes that take place in air or any gaseous medium while sound propagates through it is adiabatic and not isothermal as assumed by Newton. Adiabatic change is a change that takes place without the exchange of heat. Sound propagates in the form of compressions and rarefactions. Compression leads to heating and expansion leads to cooling as the sound propagates through the gas. Laplace pointed out that pressure variations in the propagation of sound waves are so fast that there is little time for the heat flow to maintain a constant temperature. Hence, these variations in pressure are adiabatic and not isothermal. For an adiabatic process, the ideal gas satisfies the relation P into V raised to the power of gamma, which is a constant, where P and V are the pressure and volume of the gas. Gamma is the ratio of specific heat capacities, ratio of specific heat at constant pressure Cp to that of specific heat at constant volume Cv. Cp by Cv of the gas. The above equation leads to delta P into V raised to the power of gamma equals to 0. This implies that P into gamma into V raised to the power gamma minus 1 into delta V plus V raised to the power gamma into delta P is equal to 0. This equation can be written as the product of P, gamma, V raised to the power gamma minus 1 and delta V equal to minus V raised to the power gamma into delta P. Therefore, P into gamma is equal to minus V raised to the power gamma into delta P by delta V into V raised to the power gamma minus 1. On further simplifying, we get P into gamma is equal to minus delta P by delta V by V. Thus, the bulk modulus of the gas is P gamma and not just P as Newton arrived at while deriving the expression. Thus, the velocity of sound in an ideal gas after Laplace's correction is expressed as V is equal to the root of gamma P by rho. Let this be equation 1. The value of gamma for air is 1.4. Substituting the values of gamma, P and rho for air in equation 1, we get the value of sound V in air as approximately equal to 331 meters per second. The speed of sound in air at standard temperature and pressure conditions thus obtained implementing Laplace's correction is in agreement with the experimental value.